Have you ever wondered what's flying through our solar system right now completely undetected? Did you know that astronomers estimate thousands of interstellar objects may be passing through our neighborhood, but we've only ever confirmed 3? When the third one, 3I divided by Atlas, was tracked, it offered a revolutionary glimpse into another star system. But just as it reached its most critical point, nearly every major Western telescope, Hubble, Webb, the VT went dark. They blinked, and in that moment, the entire story of astronomy changed. When the announcement finally came out of Beijing, it stood apart from typical scientific communications. China's latest report on the interstellar object 3I divided by Atlas was concise, technical, and unambiguous in its conclusions. It did not present new detections so much as it verified previous analysis. The document confirmed with high confidence that 33 divided by Atlas was an interstellar object characterized by a hyperbolic trajectory and an atypical chemical composition dominated by carbon dioxide. In its carefully translated summaries, one phrase drew particular attention. Nothing about the object has changed, and yet everything has. For a report of this nature, the wording was unusual, measured, but reflective, suggesting that while the data remained consistent, the implications for astronomy had grown significantly clearer. For months, astronomers around the world had tracked this strange traveler moving through the solar system, an icy, fast-moving body that wasn't from here. At first, it was a curiosity. Then, it became an obsession. By the time China's data reached the international community, 37 divided by Atlas was no longer just another interstellar comet. It had become a mirror reflecting both the limits of human observation and the new balance of scientific power on Earth. Let's back up. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, picked up a dim moving speck of light from its Chilean telescope array. At first, analysts thought it was just another comet, but its trajectory refused to fit the pattern. Within days, orbital calculations confirmed that it was not bound to the sun's gravity at all. Its path was open-ended, hyperbolic. It had come from outside the solar system, would pass through once, and disappear forever. The object was officially named 3I divided by Atlas, the third interstellar visitor ever observed, following in the cosmic wake of the mysterious Oumuamua in 2017 and Boris in 2019. Each of these rare bodies had arrived without warning, streaking across the solar system at impossible speeds. To scientists, they were precious frozen messengers, carrying chemical fingerprints from other stars. But unlike its predecessors, 3I divided by Atlas appeared just as human systems faltered. Its timing would expose the fragility of our supposedly global view of the sky. At first, everything unfolded as planned. Telescopes across both hemispheres locked onto the newcomer. Hubble took optical images. The James Webb Space Telescope, orbiting far beyond Earth's atmosphere, analyzed it in infrared. Ground-based observatories from Hawaii to the Canary Islands joined in, recording its changing brightness. Early estimates placed its heliocentric velocity at more than 29,000 kilometers per hour. That's roughly 130,000 mph. The object was on a steep trajectory through the inner solar system, heading toward the sun's glare, before it would sling outward again toward the stars. As the weeks passed, the data revealed strange behavior. Most comets brighten as water ice sublimates, turning directly from solid to gas when they approach the sunday. But this one didn't behave that way. Spectral readings showed that its coma, the diffused halo of gas surrounding the nucleus, wasn't dominated by water at all. It was carbon dioxide $CO2 glowing faintly through the vacuum. Water, the main driver of cometary activity in our solar system, was almost absent. That single fact alone suggested 3I divided by Atlas had formed in an entirely different kind of environment, perhaps in the frozen outer regions of another star system. This is one of the object's most profound mysteries. Our solar system is relatively water-rich. An object built primarily from carbon dioxide ice implies it formed in a place much colder, or perhaps where the chemical ratios were fundamentally different from our own. It's a direct piece of evidence that the building blocks of planets elsewhere are not necessarily the same as ours. Then, just as the comet reached its most revealing phase, its closest approach to the Sun, Earth, blinked. In late September, for 36 hours, nearly every major Western observatory went dark. Hubble paused for a scheduled gyroscope realignment. The James Webb Space Telescope began a planned instrument switch, a procedure that required over a day of thermal stabilization. In Chile, the Very Large Telescope entered its maintenance cycle, its massive mirrors undergoing cleaning. Gemini North and South switched to pre-approved planetary studies. Each action on its own made perfect sense, but together they created something rare, a global blind spot. The timing could not have been worse. During that exact window, 3I divided by Atlas crossed the region of the sky, perilously close to the sun's glare. Observing from Earth became nearly impossible without specialized equipment. With every hour unobserved, scientists risked losing critical data about its outgassing rate, coma evolution, and chemical composition. To the public, the pause went unnoticed. But to astronomers, it was devastating. A hole in the light curve of an object that would never return. Except, as it turned out, the sky wasn't silent everywhere. Across the Pacific, China's high-altitude observatories in Tibet, Qinghai, and Yunnan kept watching. Their schedules unaligned with Western institutions left them free during the blackout. Their clear, dry air, thinner and colder than most sites on Earth, allowed continuous optical and infrared coverage. While the world's largest telescopes paused for recalibration, a network of smaller instruments on Asia's roof recorded the only uninterrupted data stream of the interstellar visitor. Each observatory followed a meticulous process. Light collected by their primary mirrors was focused onto cooled CCD sensors, each exposure lasting between 30 and 120 seconds. At the comet's blistering speed, longer exposures risked motion blur. Every frame was time-stamped within a millisecond using GPS clocks and stored in the standardized FITS format, which preserved not only the image but also its metadata, coordinates, filters, temperatures, and environmental readings. These files were transmitted through fiber optic links to centralized servers in Nanjing and Beijing, where redundancy systems maintain power despite sub-zero temperatures. The engineers called them servers under ice. By the time Hubble and JWST came back online, 3I divided by Atlas had already moved more than 1 million kilometers along its path. That's over 620,000 miles. Without those Chinese data, scientists would have faced positional uncertainty so large that reacquiring the comet might have required blind scanning. Instead, China's observations allowed the rest of the world to realign. The mountain observatories had filled in the gap with extraordinary precision, providing continuous measurements of brightness and position that stitched the global timeline back together. The results were remarkable. Over the 36-hour blackout, 3I divided by Atlas brightened by about a third of a magnitude. A modest increase, but enough to indicate a spike in activity. Its coma elongated toward the sun, suggesting a jet of gas and dust erupting from the nucleus. Later analysis showed that the dust particles were unusually large and carbon-rye, a combination rarely seen in comets born within our own solar system. This carbon-rich dust combined with the carbon dioxide ice painted a consistent picture of an alien environment. It wasn't just a curiosity, it was a coherent chemical story. The object was a fragment from a system where carbon, not water, dominated the icy chemistry, fundamentally challenging our assumptions about what average comets look like across the galaxy. As the data circulated, it became clear that something profound had occurred, not just astronomically but geopolitically. For decades, the world's great observatories funded by Western consortia had defined the boundaries of astronomical truth. Now, for the first time, the most critical observations of a historic interstellar event came from elsewhere. The instruments that mattered most were not the biggest or most expensive. They were simply the ones that stayed awake. Still, the question of trust lingered. Merging Chinese data with Western datasets required careful calibration. Differences in software, wavelength alignment, and phototrick scales had to be reconciled. A Chinese scientist documented every step. Brightness was calibrated using Land-Alt standard stars. Magnitudes cross-referenced with a Sloan digital sky survey, and spectral lines corrected using thorium and neon lamps. Independent verifications by teams in Hong Kong and Taiwan confirmed the measurements within tight margins of error. Once combined, the global data set reached unprecedented precision. Astrometric accuracy within a 150th of an arcsec, eccentricity fixed at 1.19. The verdict was irrefutable. 3I divided by Atlas was an interstellar object. Beyond the numbers, though, the event highlighted an uncomfortable truth about modern astronomy. For all its talk of international cooperation, the system remains uneven. Of the world's 30 largest telescopes, those with mirrors over 6 meters or 19 ft in diameter, 2.3 are located in the Americas or operated by Western partnerships. China's telescopes are smaller, typically between 2 and 4 about 6.12 to 13 ft, but their strength lies in automation and distribution. Multiple mid-size instruments working in tandem can outperform a single giant one when timing and coordination matter more than sheer sensitivity. Large telescopes are designed for depth, to peer into the faintest galaxies billions of light years away. But smaller observatories excel in continuity, watching the same patch of sky hour after hour. For transient or fast-moving targets like 3I divided by Atlas, that constancy can be more valuable than aperture. This highlights a fascinating, almost paradoxical mystery in modern science. We've built billion-dollar mega-instruments capable of seeing the dawn of time. Yet these incredible tools are vulnerable to simple scheduling conflicts and routine maintenance. The real mysterious factor 3I divided by Atlas exposed wasn't in space but on Earth, a systemic lack of coordination, a fragility in our centralized approach. It teaches us that data isn't just about power, it's about presence. During the blackout, China's robotic scheduling software reassigned telescopes in real time as weather and target angles shifted. By stacking hundreds of short exposures and co-adding the data statistically, the network achieved a signal-to-noise ratio rivaling that of much larger Western instruments. Persistence, not size, became the decisive factor. But metaphorically, it measures axis. Who gets to see and record the universe? For decades, the largest apertures have been symbols of prestige and control. The 3I divided by Atlas campaign inverted that relationship. The most complete record of a cosmic event didn't come from the largest mirrors. It came from those willing and able to keep observing when others paused. When the final combined analysis was released, the language was careful but unmistakable. The data confirmed that 3I divided by Atlas was composed primarily of carbon dioxide ice, that it had originated outside the solar system, and that it passed through on a one-time trajectory before heading back into interstellar space. But there was something else beneath the surface of those conclusions. A recognition that the discovery marked a turning point. For decades, the Western scientific community had been the unquestioned keeper of cosmic truth. Now the chain of observation was global and the links had shifted. A single blackout had shown how fragile centralized knowledge can be. The universe, after all, doesn't care where telescopes are built. It reveals itself only to those who happen to be looking at the right time. In the months that followed, 3I divided by Atlas faded into the darkness, its trail thinning as it receded from the Sunday. Its story, however, remained vivid, an object from another star system captured in fleeting detail thanks to the persistence of a few observatories on remote mountain summits. The data confirmed what everyone suspected, but few had truly grasped that the cosmos is porous, restless, and connected in ways we are only beginning to understand. China's final report closed on a line that sounded less like science and more like reflection. Nothing about the object has changed, and yet everything has. It was a statement about the comet, but also about us. The discovery had not revealed aliens or danger or hidden messages in the stars. It had revealed something subtler and perhaps more profound, that the boundaries of exploration are shifting, that truth in science now depends on shared vigilance, and that the universe continues to speak in signals we can only hear when someone somewhere refuses to blink. For 36 hours, half the planet looked away. The other half didn't. And in that narrow window, humanity's newest messenger from the stars whispered its story into the record, unseen but not unheard. A fragment from another sun passing through ours, carrying the quiet confirmation that we are far from alone. The most valuable lesson here isn't just about comets. It's about perspective and persistence. It teaches us that the biggest discoveries don't always come from the biggest or most expensive instruments. Sometimes the most critical factor is simply being present. True insight often comes not from having the most power, but from having the vigilance to keep watching when everyone else is scheduled to look away. In science and in life, persistence is often more powerful than prestige. What do you think this shift means for the future of astronomy? Do you believe we are truly ready for a fully global cooperative scientific community, or will competition always get in the way? Let me know your thoughts in the comments below. And if you enjoy deep dives into the changing cosmos, don't forget to subscribe.